This is John Whitaker for the Mathematical Analysis 2 class, and this is our 16th video lecture. And today we're going to do two theorems having to do with Riemann-Stieltjes integrability. One is an extension of a previous theorem that we had done, and it involves a series of real numbers. And the second one is a theorem that relates Riemann-Stieltjes integrability to just Riemann integrability, and a formula that relates the two. So here's the first theorem. It says, suppose C sub n is greater than or equal to 0 for 1, 2, 3, forever. This is n equal to those numbers. And the sum of the C sub n's is n run from 1 to infinity, converges. Suppose that S sub n is a sequence of distinct points in A to B, and alpha of x is equal to the sum, as n runs from 1 to infinity, of C sub n times the step function acting on x minus S sub n. We're also going to let f be continuous on A to B, then the conclusion is that the integral from A to B of f d alpha is equal to the sum, as n runs from 1 to infinity, of C times f of S sub n. Here's proof. For each fixed x element of A to B, this sum is n runs from 1 to infinity of C sub n times I sub n acting on x minus S sub n is a convergent sequence of real numbers. I should say convergent sequence, convergent series of real numbers. Okay, the reason that this is due to the fact of the comparison test which we will cover in chapter 3, okay? But that's what it's really due to. Now, let us let x sub 1 be less than x sub 2. Then, for each n, you note that 0 is going to be less than I of x sub 1 minus S sub n, which is going to be less than or equal to I of x sub 2 minus S sub n. And so, since C sub n is greater than 0, greater than or equal to 0, we have
C sub n times I of x sub 1 minus C sub n is going to be less than or equal to C sub n times I evaluated x sub 2 minus S sub n. Thus, if you define alpha, or look at alpha of x sub 1, that's going to be equal to the sum as n runs from 1 to infinity of C sub n times I sub n of x sub 1 minus S sub n. That's going to be less than or equal to the sum as n runs from 1 to infinity of C sub n times I, shouldn't be I sub n, it's just I. Yeah, I call it I sub n. Yeah. I shouldn't be calling it I sub n, it should just be I. So go back. Sorry. Make this small change here in notation. Just a step function, we just call it I. This should just be I. And here it's x2 minus S sub n. And this is alpha of x sub 2. So what this is saying is that alpha, as we've defined it in the statement of the theorem, that alpha is going to be monotonically increasing. Let me write that up. Thus alpha of x is, or just alpha, is a monotonically increasing function on A to B. Now, note, alpha of A is going to be equal to 0 as I of A minus S of n. That part is going to be 0, and that's for all n. Also, alpha of B is going to be equal to the sum of the C sub n, is n runs from 1 to infinity, as I acting on B minus Sn is always equal to 1 for all n natural numbers. We use J to represent the natural numbers in this group. Next, we're going to let epsilon greater than 0 be given. Then, the sequence of partial sums, S of n running from 1 to infinity, which equals to the sum as k runs from 1 to n of the C sub n's. Here, I should say k. K. C sub n should be C sub k. K running from 1. Yeah, just this. No, this should be n here. I made a mistake. N running from 1 to 50. Okay, that's what that is. This is an increasing sequence of real numbers. The reason it's increasing is you're summing up more and more positive numbers as n gets bigger. Well, non-negative numbers. As c sub k is greater than or equal to 0. So this sequence of partial sums is a monotonic sequence. And we know that it converges because the c sub n's, the series converges. And so what it converges to is it's suprema by the monotone convergence theorem. Let me write that. So this is an increasing sequence of real numbers, this partial sums, that converges. So, if you will, S of n converges, the sequence of partial sums, to the soup of all the S of n's, which we'll call S, which is equal to the sum as n runs from 1 to infinity of c sub n. That's what this guy converges to. So, there exists an n that's an element of the natural numbers, such that for all n bigger than or equal to this big N, S minus this sum, as k runs from 1 to n, of c sub k will be less than epsilon. So, that means that the sum as k runs from 1 to infinity of c sub k minus the sum as k runs from 1 to big N, because big N is bigger than or equal to big N, of c sub n will be less than epsilon. So what that says is that the sum as k runs from n plus 1 up to infinity of c sub k, that has to be less than epsilon because that's what this part is. Now, what we're going to do is we're going to put alpha sub 1 of x, that's going to be equal to the sum as n runs from 1 to big N of c sub n times I acting on x minus s sub n. And we're going to let alpha sub 2 be equal to the sum as n runs from n plus 1 to infinity of c sub n I of x minus s sub n. That's alpha sub 2 of x. Now, next thing we want to do is we're going to note by previous theorems by previous theorems. Here's what we have. What we get is that the Riemann-Stieltjes integral from a to b of f d sub alpha sub 1 is going to be equal to the sum as I runs from 1 to n of c sub I f s sub I. Or we can make this n and be consistent. And the way we can see that, so a parenthetical part of the explanation here, is alpha sub 1 can be thought of as C1 times B1 plus C2 times B2 plus all the way up to Cn times Bn, where the Ci's are just numbers, but the Bj, I'll call them, are equal to the step function evaluated at x minus s sub j. And the interval from a to b of f d alpha sub 1 would be equal to the sum as j ran from 1 to n, big N, of the interval from a to b of f times this d of cj bj. That's what we have. By an extension, really, a theorem we've already done. And that's by another extension of the theorem we've already done, will be the sum as j runs from 1 to n. All this parenthetical expression, explanation. Of cj, interval from a to b, of f, d, bj. And this would be equal to the sum, as j runs from 1 to n, of cj, and then this interval every time would be f of s of n. By extension of previous theorem. No, that's a direct application of previous theorem. So we know the integral from a to b of f d alpha sub 1 exists because we're assuming that f is continuous. And so we had a previous fact that tells us that if you're continuous, then your Riemann still disintegrable with respect to alpha. Okay, so that is the parenthetical explanation. That's why we get this results. Okay. Now, let's look at alpha sub 2. Note that alpha sub 2 of A, well, it's going to be 0, and alpha sub 2 of B, well, it's going to be the sum as we run from n plus 1, n equals n plus 1, to infinity of the Cn's, which we know this to be less than epsilon. So, alpha sub 2 of B minus alpha sub 2 of A is going to be less than epsilon. Now, since f is continuous, then the integral from a to b of f d alpha sub 2, it exists. And by a previous fact, the integral from a to b of f d alpha sub 2, well, that's going to be inside absolute values. That's less than or equal to m times alpha sub 2 of b minus alpha sub 2 of a, where m is equal to the supremum of the f sub x. x element of A to B. But we know that this guy is less than epsilon, so we'll work with that in just a second. So since alpha is really equal to alpha 1 plus alpha sub 2, those are functions of x, where x is an element of A to B, okay? Then this integral from A to B of f d alpha, that integral will be equal to the integral from A to B of f times d alpha sub 1 plus alpha sub 2, which is the same thing by a previous theorem. It's the integral from A to B of f d alpha sub 1 plus the integral from A to B of f d alpha sub 2. So, what we have is the integral from A to B of f d alpha minus the integral from A to B of f d alpha sub 1. That's going to be equal to the integral from A to B of f d alpha sub 2. What's equal to? So, the absolute value of the difference between the integral from alpha b of f d alpha minus the integral from A to B of f d alpha sub 1 is going to be equal to the integral from A to B of f d alpha sub 2, which is less than or equal to m times epsilon. Really strictly less than. Okay? So, that says that the integral from A to B of f d alpha minus the sum, so this part right here is the sum, as we look at n running from 1 to big N of C sub n, f of S sub n, that is going to be less than or equal to m times epsilon. And this is inside absolute values. So, what that says, that the sum, as little n runs from 1 to infinity, of C sub n, f of S sub n, equals to the integral from A to B of f d alpha. It's because this is a sequence of partial sums. I'll write that down. Where we look at the sum as n runs from 1 to big N of C sub n f of S of n is a series of real numbers. So essentially, this is a sequence of partial sums here. We call it S of big N. And what we're showing here is that it'll be less than, it's really less than or equal to any number we want because of this quality. So any positive number that we want. And because that happens, that this is less than that, that this inequality is less than that, that says that the sequence of partial sums will converge to this particular number. And so that ends the proof. Okay, there's only one other theorem we want to do today. here's that theorem. And this relates Riemann-Stieltjes integrability to Riemann integrability in this setting. So we assume alpha is increasing monotonically and alpha prime is Riemann integrable on A to B. We let F be bounded. Okay, on A to B. Then F is going to be Riemann-Stieltjes integrable with respect to alpha if and only if F times alpha prime is Riemann's integrable on A to B. In this case, the integral from A to B of F d alpha will be equal to the integral from A to B of F of x alpha prime of x dx. So that's how we can relate Riemann-Stieltjes integrals in this setting to Riemann integrals. Oops. So we'll start the proof. We're going to let epsilon be greater than 0 be given. Since alpha prime is Riemann integrable, then there exists a partition of A to B such that the upper sum between of F, the upper sum with this partition and alpha prime minus the lower sum with this partition and alpha prime, that's going to be less than epsilon. Yes. We will denote this partition by x of 0, x of 1, all the way up to x of n. Now, since alpha is differentiable, okay, on the closed interval from A to B, then by the mean value theorem, there exists, let's say, t sub i's that are elements from x sub I minus 1 up to x sub I for this partition, such that alpha prime acting on t sub I times x sub I minus x sub I minus 1, that will be equal to alpha of x sub I minus alpha of x sub I minus 1. Or, what this says is that alpha prime of t sub i's times this quantity right here is the delta x sub i's that would be appearing in Riemann sums would be equal to, here is Riemann-Stieltjes sums delta alpha sub i's. That's what these are for this particular partition. Okay. Now, if we just let S sub i's also be numbers in x sub I minus 1 up to x sub I, then by a previous theorem, it was in this chapter. Applied to alpha prime being Riemann integral, we have that the sum, as I runs from 1 to n, of the absolute value of alpha prime of S sub I minus alpha prime of T sub i's, that will be less than epsilon. And that's because the upper sum minus the lower sum was less than epsilon, and that's by a previous theorem. Now, again, we're going to let m equal to the soup of all the f of x's. X is an element from A to B. Okay. Then we observe that the absolute value of the sum as I run from 1 to n of f of S sub I times delta alpha sub I minus the sum as I run from 1 to n of f of S sub I times alpha prime S sub I, alpha prime of S sub I, times delta x sub I, these quantities inside absolute values. Is equal to, okay, so it's the sum as I runs from 1 to n of f of S sub I. Here, this quantity right here would be alpha prime of T sub I times delta x sub I by our previous work on the other board for the partition we're looking at, minus the sum as I runs from 1 to n of f of S sub I, alpha prime evaluated S sub I times delta x sub I, and we can combine these two summations. And so we get that this is equal to the sum as I run from 1 to n, so I have to value this, of f of S sub I, and then times alpha prime of T sub I minus alpha prime of S sub I, and then times delta x sub I. All right, now, using the triangle clause, bringing this inside, extension of the triangle clause, the absolute values inside. Here, we have the absolute value of f of S sub I. It would be times the absolute value of a prime of T sub I minus a prime of S sub I, and the delta of x sub i's are positive, so I won't put them in absolute values. And then that's going to be less than or equal to, this guy's always less than m, which is the supremum. And here, this is of absolute value of a prime of Ti minus alpha prime, I should say, of evaluated S sub I times the delta X sub I. Then we pull the m outside, because it's a constant. Sum 1 to n of the absolute value of f prime, alpha prime of ti minus alpha prime of si times delta si. But I know this part's less than epsilon, so I think that's going to be able to help us. And that is indeed what we're going to do next. Is make that substitution for epsilon. So that sum was less, this particular sum was less than epsilon. So we have that this is less than m times epsilon. Well, since, for our result here, that the absolute value as I runs from 1 to n of f of s sub I delta alpha sub I minus the sum as I runs from 1 to n of f of si times alpha prime evaluated as si times delta si is less than m times epsilon, then coming up with an inequality that doesn't involve absolute values, what we have is this sum here, original sum, first sum, okay, will be less than m times epsilon can be plus the second sum. And so, what that yields is that the sum as I runs from 1 to n of f of s sub I delta alpha sub I will be less than m times epsilon plus, okay, so here, this is going to be the upper sum with p f alpha prime. It'll be this is going to be less than this. The upper sum with the partition we had and now m times alpha prime. Okay? Because this upper sum is going to take the maximum value over the subintervals created by this partition. And that's what's going to happen. And this is particular, well, it's for any S sub I values that we have. So this is true for, let me just say this is true for all choices of S sub I that are elements from x sub I minus 1 up to x sub I. Okay. Thus, upper sums P F alpha is going to be less than or equal to the upper sums P F alpha prime plus m times epsilon. That's what we have. And so what that tells us similarly, since the absolute value between the sum as I runs from 1 to n of f of s sub I delta alpha sub I minus the sum as I runs from 1 to n of f of s sub I alpha prime of s sub I times delta x sub I, that guy, since that is less than epsilon, or m times epsilon, then looking at the other part of this inequality we can get involving a statement without the absolute values, what we have is minus m times epsilon at the left-hand side, and it will be plus well, let's just say it's going to be less than or equal to this sum. I run from 1 to n of f of s I delta alpha sub I minus this other sum. Sum as I run from 1 to n of f of s I alpha prime of s I delta x I. That's what we have. And so that says that this sum, as I run from 1 to n, of the f of s sub I, alpha prime s sub I, delta xi, that will be less than or equal to, so I'm taking this guy and adding it to both sides, and now I'm going to add m times epsilon both sides. So it's this sum as I runs from 1 to n of f of si delta alpha sub I plus m epsilon. So what that says is this sum as I runs from 1 to n of f of s sub I alpha prime of s sub I delta x sub I is going to be less than or equal to, just less than really, oh, this could be just less than, the upper sum with the partition that we're using of f alpha plus m times epsilon. Okay. And that's true for all choices of s sub I that's in the subinterval x sub I minus 1 up to x sub I. So that says that the upper sum of p f alpha prime, that's the Riemann upper sum, not the Riemann-Stieltjes, is going to be less than or equal to the upper sum, this is the Riemann-Stieltjes upper sum, with the partition f in alpha, plus me, m times epsilon, I should say. Therefore, of the two similar type steps we've done here, what we have is that the absolute value of the upper sum, f, with the partition f and alpha, minus the upper sum with partition and f alpha, this should just be alpha. this should be the Riemann upper sum, okay, with F alpha prime. And here is the Riemann-Stieltjes upper sum with this partition F with respect to alpha. That's going to be less than or equal to M times epsilon. The above work will hold true for any refinement, let's say P star of phi consequently get the same result here using P star. So let me write that over here. So consequently, since we have this upper sum of P star F alpha prime, so that's the Riemann sum, minus the upper sum with P star F alpha, that's the Riemann-Stieltjes sum, is less than or equal to M times epsilon. Then that means that the absolute value of the upper Riemann-Stieltjes, upper Riemann integral with F alpha dx minus the upper Riemann integral with F Riemann-Stieltjes integral of F with respect to alpha, that is going to be less than or equal to M epsilon. And so since epsilon is arbitrary, what that's going to force is that these two things have to be the same. So they equal each other. So the upper Riemann integral equals to the upper Riemann-Stieltjes integral in this case. Okay. Now, still got a little bit more work to do to prove what we want to, and that work is analogous to what we just did, except instead of working with the upper sums, we're going to work with the lower sums. Okay, so here's what I'll say. Similarly, since the sum as I runs from 1 to n of f of s sub I times delta alpha sub I, that it's going to be less than m times epsilon plus the sum as I run from 1 to n of f of s sub I, alpha prime of s sub I, and delta x sub I. Then, what that gives us is that the lower sums, p, f, and alpha, will be less than m times epsilon plus the sum as I run from 1 to n, f of s sub I, alpha prime of s sub I, times delta x sub I. And that's true for all possible choices of S sub I, elements of x sub I minus 1 up to x sub I. Thus, what we get is that the lower Riemann-Stieltjes sum is going to be less than or equal to m times epsilon plus, this is the lower, this is the Riemann sum between f, this partition, f alpha prime. Also, since the sum as I runs from 1 to n of f of s sub I, alpha prime of s sub I, times delta x sub I is less than, so let me just write down here, is less than m times epsilon plus the sum as I runs from 1 to n of f of s sub I delta alpha sub I then what we get is that this lower sum, Riemann sum, with this partition of the function f times alpha prime will be less than m times epsilon plus sum as I run from 1 to n of f of s sub I delta alpha sub I for all possible choices of S sub I elements from x sub I minus 1 up to x sub I, these subintervals of our partition. This, the lower Riemann sum with this partition f alpha prime is going to be less than or equal to m sub epsilon plus, here this is going to be the lower Riemann-Stieltjes sum with this partition f and alpha. So that gives us that the absolute value between these lower sums one Riemann sum on one Riemann-Stieltjes is less than m times epsilon. So the above work is true for any refinement of P, say P star. So here's what we get. We're almost done. So since we have the absolute value P star F alpha prime minus the lower Riemann-Stieltjes sum with P star F with respect to alpha is less than or equal to m times epsilon, then that's going to force this lower Riemann integral minus this lower Riemann-Stieltjes integral with respect to alpha to be less than or equal to m times epsilon. And since epsilon greater than 0 was arbitrary, that says that the lower sum of A to B of f alpha dx, f alpha prime dx, equals to the lower sum of f d alpha. Okay. So, that means that f is Riemann integrable if and only if f is Riemann-Stieltjes integral if and only if f times alpha prime is Riemann integrable. Because their lower integrals are the same and their upper integrals are the same as each other. And so if for any particular f or f alpha prime, that it's, for f, if its lower integral is equal to its upper integral, then that's going to force the lower integral for f alpha prime to be equal to the upper integral for f alpha prime, because they're the same, and vice versa. And that's the proof. Thank you very much for your time and patience. That concludes this lecture.